Good evening, everybody. Welcome to BrisScience October 2025, and we have a fantastic packed house tonight. So great to see you all here. I am your MC for this evening, Joel Gilmore, and if this is your first time, welcome to BrisScience, a series of free public lectures on science held once a month here at the fantastic Edge at the State Library of Queensland and presented by the University of Queensland. We are so excited to have you all here tonight. I would like to start by acknowledging the traditional owners of the lands on which we're meeting tonight and pay my respect to elders past and present. It's a great time to reflect that the First Nations cultures of Australia have a history going back 65,000 years, which includes going back into the last glacial period or ice age, where sea levels were 100 metres lower than they are today. And having gone through that transition, there are still stories that we can learn from today as in the sciences that we do now. So, little bits of housekeeping before we get started. If you've got a mobile phone, a great opportunity to turn it to silent, but also a great opportunity to scan this QR code. Not that one, wait for it. It's a great moment. That QR code there. I jumped the gun on the fantastic IT team there. So tonight we are going to be taking questions over the app after our talk, and we would love for you to put in all of your questions, comments and ideas, and then afterwards we'll go through as many as we can. If we can't get through them all, we will have an opportunity for you to chat with our speaker later in the evening. We'll have some food and drink. We'd love you to stick around and celebrate all the fantastic culture, and yes, there will be ice for your drinks. Can't back that up. Because, of course, tonight's talk is about Antarctica and the oceans. It's my great pleasure to welcome Professor Helen Bostock, who is an ocean explorer based at the University of Queensland. And she regularly voyages to Antarctica to study the physics, chemistry, biology and geology of the oceans there and their interaction with the world's climate. We are so excited to have her here tonight to talk about her research, her adventures, and perhaps some thoughts on what we might have in store for us in the future. And that's just the tip of the iceberg. Thank you. Can you please put your hands together? Welcome, Professor Helen Bostock.
All right, good. The sound is working. Well, how can I follow on from such an intro? I'm so excited to see so many people in Queensland are interested in Antarctica. It's so far away from our tropical, subtropical 30 degrees that we were experiencing today, and yet you're here to hear about the icy continent, so that actually really warms my heart and hopefully doesn't melt too much ice. So today I'm going to kind of bit of background in why we care about Antarctica, and then talk to you about a voyage we did in 2023, in the summer of 2023, where we went down to Antarctica, and I'll show you some of the work we've been doing since then on the results from that voyage, which are really hot off the press. All right, well, I would first also like to start with an acknowledgement of country, and as Joel said, our Indigenous owners of the land have been studying the environment for a lot longer than we have, and we have a lot to learn from them. And there are even some stories about Indigenous Polynesians and others maybe making it down to Antarctica well before Europeans. So we're sitting here in Brisbane. Why do we care about what's happening way, way to the south of us? Why do you care? Anyone? Climate change? Anyone? Because it's cool? Okay. Anyone else? At the back here? It's nice, okay. Ocean currents? What was it? You said food cycles, yes, so about the biology. Anyone care about the penguins? Yes. Usually when I ask that question, most people say we care about the penguins, so I'm kind of surprised. You guys have let me down. Not enough penguins and penguin lovers in this audience. Why do I care about Antarctica? Well, I'm a climate scientist and oceanographer. And actually, I study the oceans to understand the climate, because the oceans are part of the climate system. Our climate system is actually made up of 5 different types of spheres. We've got the atmosphere, which we all know about, that we experience regularly with our weather and climate daily. We have the hydrosphere, which is the ocean, the water. The cryosphere, which is the ice. And I'll be talking mostly about the hydrosphere and the cryosphere today. Then, of course, there's the biosphere, which I will touch on slightly, even though I'm not really a biologist. I will touch on how the biology of Antarctica is influenced. And, of course, then the geosphere as well, which is the geology and the underlying plate tectonics and things that's happening. And these all make up what we call the climate system. So it's a complex system. It's made up of lots of different things interacting. And the cryosphere, which we're going to talk about today, the ice, is one of the least known parts of the climate system because it's so hard to study. Why do we care? Well, about Antarctica in particular, because it actually has a significant influence on the global climate. It influences our sea level. It influences how moderate our climate is. And of course, it influences those penguins and the polar ecosystems. So I'm particularly interested in the ice-ocean interactions and how that influences ocean circulation and climate. So that's what I'm going to focus on today. So when I'm talking about the cryosphere, there are lots of different parts to it. It's anything to do with ice. But in particular, in Antarctica, we're interested in the ice sheet, the ice shelves, where it leans out over the ocean, and the sea ice. So those parts of the system are what we're going to talk about today. This is a satellite image of Antarctica. 98% of it is covered in ice. So the majority of it is covered in ice. That ice is an average of 2 kilometers thick. So it stores a huge amount of water. And if we melted all of Antarctica, it's equivalent to raising sea level up to 58 meters. So that's a lot of water. 70% of all fresh water on Earth is stored in the Antarctic ice sheets. So this is a really massive part of the cryosphere system. Now, there are 2 ice sheets. We have the West Antarctic ice sheet and the East Antarctic ice sheet. And they're separated by the Transantarctic mountains that cut through the middle. And the East Antarctic ice sheet is where most of that water is stored. 90% of the water and ice is in the East Antarctic ice sheet. The West Antarctic ice sheet is significantly smaller. However, the ice sheets... Oh, it didn't work. My animation didn't work. Ooh, don't know how we do that. We can see that based on this graph... Oh, there we go. Thank you. Obviously, it's controlled elsewhere. We can see that the ice sheet is melting. And so this animation shows you, with the graph, with the time series along the bottom, we can see where the ice sheet is melting most. So we have areas in red where there's significant ice melt, and areas in blue where we're actually gaining ice. But overall, we're actually losing more ice than we're gaining right now. And so we can see that most of that ice loss is actually in West Antarctica, and there's a small amount of ice loss in East Antarctica. That's a good thing, because West Antarctica has a lot less water and ice than East Antarctica. And so it's only about maybe 6 to 10 meters of sea level rise only. We'd probably be underwater here if we had 6 to 10 meters of sea level rise in West Antarctica versus the rest is in East Antarctica. So why is West Antarctica melting more than East Antarctica? So on the left here, we have the amount of melt, average, that I just showed you the animation. In the middle, we have sea surface temperatures around Antarctica. And on the right, we have the bedrock of Antarctica. So this is your ice-ocean interactions here with the geology. We can see that based on the sea surface temperatures, or actually these are the seawater temperatures in general, we can see that around West Antarctica, the temperatures are much, much warmer. We can see these orange and yellow colors, so they're much warmer. And that's the reason why West Antarctica is melting more than East Antarctica, because warm water is able to interact directly with the ice and start melting it. We can also see on the bedrock map, that actually most of West Antarctica is below sea level. So that allows the seawater to flow right underneath the ice sheet and melt it from below. So a lot of the melting that's going on is not happening from above. The atmospheric temperatures are still quite cold. A lot of that melting is happening from underneath the ice sheets. That's very hard to measure, but we have some new techniques now to measure these things using satellites and changes in the thickness of the ice sheets. But a lot of what we need to do is still get down there on ships and actually measure the changes down in Antarctica. But what happens when the ice sheets melt? Well, the consequence is global sea levels rise. So this is the global sea level rise over the last century or so, and we can see that it's ramping up. And these are also measured from satellites, but also tide gauges around the world. So it's rising at about 4 millimeters per year, and it's increasing its rate. Now, most of that sea level rise is from ocean expansion, or heating the water and expanding the water. Some is coming from Greenland, but more and more of this sea level rise is a contribution from Antarctica, from these melting ice sheets. What about sea ice? If sea ice melts, it doesn't raise sea levels, so it's a separate problem. Why do we care about sea ice? Well, in summer, this is what sea ice looks like. It sort of melts right back, and we only have a little bit of sea ice. But in winter, sea ice expands massively, and actually expands the size of Antarctica up to 3 times. So the total size of the ice around Antarctica is 3 times its size in winter. The orange line there is the average extent of sea ice over a 30-year time period. So we can see that in 2019, September 2019, it was a bit less than the average. We can see that the ice didn't quite make it to the edge of the average. This is what sea ice looks like when it starts to form. It's called pancake ice. So it forms in these small, and then it just grows out. And it's very thin and flat, basically just a few centimeters thick at the start. And then it slowly builds up and starts attaching to each other and building these big, big ice sheets. Now, why do we care about sea ice? We care about sea ice because it reflects a lot of the solar energy, solar insolation that is coming in to the Earth. So 85% of all solar radiation or solar energy that hits the ice is directly reflected back out to space. So it keeps the globe cool. In contrast, the ocean only reflects 7% of that solar radiation and absorbs 93%. So if we start losing that sea ice, we're going to start absorbing a lot more of the solar radiation coming in because we've now exposed a lot more ocean, and it's dark relative to sea ice. Sea ice is light and reflective. Now here's an illustration I like to use because here, this is from Canada. There was a leaf sitting on top of the ice, and you can see that when the sun hits the leaf, it has warmed up the leaf, but it's melted the ice directly underneath. But when the sun hit the surrounding ice, it reflected the heat away and didn't heat up. and left the ice behind, leaving a really nice imprint of the leaf. So the whole point of albedo is by having lighter surfaces, it reflects more of that energy back out into space, and the Earth heats up less. Here's the current situation of sea ice. So this is August 2025, and we can see on the right there that relative to the average, so that same average that was drawn on the previous figures, we can see that we're significantly less than the average from that 30-year period. A little bit more in the Ross Sea sector, but mostly less around the rest of the continent. And we can see the anomalies through time. We were cruising along, fairly highs and lows, a few anomalies either side, but around 2015, 2016, suddenly we took a big dive, and we haven't really recovered the sea ice ever since. It's just been continuously below average for the last decade or so. We also care about the sea ice because it impacts the biosphere, the biology. So Antarctica, there's not actually that much that lives on the land, maybe a few mosses and things. Most of the biology and the ecosystems around Antarctica actually live in the ocean. They live on or under the sea ice. And so we have this really complex, very productive ecosystem that lives in that sea ice zone. And so if we lose the sea ice, we're going to start changing how that ecosystem will function. All right, so that's enough background. I'm going to talk to you more about what we've been doing and what we're interested in. So I told you I'm interested in ice-ocean interactions. So our ice shelf and our ice sheet is off to the left, and our deep, deep ocean is off to the right. So what happens is the waters flow onto the shelf. These warmer ocean waters flow onto the shelf, warmer relative to the sort of Antarctic temperatures. So maybe 2 degrees, but when most of the water around Antarctica is minus something, minus 0 to minus 2, then 2 degrees is relatively warm. And so these warm waters flow onto the shelf from the open ocean, and they go under that ice sheet, and they start to melt under the ice sheet. But as it melts, that water becomes fresher, mixes with the melting water, becomes fresher, and much, much cooler. And we call this ice shelf water. Super cooled ice shelf water. At the same time, we also have sea ice forming in front of the ice shelf. So we have our pancake ice forming. And as it forms, the sea ice actually rejects the salt. So sea ice, if you tasted it, and I have, it's only slightly salty. Most of the salt is left behind in the ocean. That makes the ocean much saltier, because you've taken up ice, but you've left behind the salt. So what happens is we end up basically forming what we call dense shelf water, and that is because as the sea ice forms, the surrounding water gets saltier, and more salt makes the water denser. It's both cold and salty. Now, that dense water then is so dense, it sinks down to the bottom and flows off the edge of the shelf, and we call that Antarctic bottom water. I realize that I've just thrown a lot of concepts at you, so we're going to break this down, and you're going to help you visualize it with what I call kitchen oceanography. All right, so maybe some of you have tested how fresh your eggs are by putting them in water. Yeah, fresh water. Now, I've put 2 eggs in 2 glasses of water here. One egg looks like it's fresh because it's sunk to the bottom. The other one is floating. If I told you 1 glass of water was warm, fresh water, and the other was cold, salty water. Now let's add in some food dye. So I've added red food dye to the water that is warm and fresh, and we can see the food dye is less dense than the water, so it's mixed very quickly. I added blue food dye to the cold water, which is slightly salty, and you can see that the food dye is less dense than the rest of the water, so it's just floating at the surface. So here we can see that the egg is floating because it's in water that is more dense than the egg. Now, if we added our blue water, which is cold and salty, to our red water, which is warm and fresh, it sinks to the bottom and would just flows along the bottom of this tank. Now that's what's happening in Antarctica. When we're forming the sea ice, we're forming very cold, very salty waters, and it sinks down to the bottom of the ocean and flows along the bottom. And as it flows off the edge of Antarctic continent, you've got these massive waterfalls of cold, dense water, salty water, flowing down to the bottom of the oceans. Now, we form sea ice all around Antarctica, but to form these really dense waters, we need a lot of sea ice production. And usually when sea ice forms, once it forms like a cap on the ocean and no more sea ice forms. But in places called polynyas, and polynya is a Russian word for an open body of water surrounded by ice. In places like polynyas, if we can play this, it's playing, you can see that during the middle of winter, if you have these big, strong winds called katabatic winds blowing off Antarctica, it continues to blow the ice that's just been formed, the sea ice that's just been formed, away from the coast. And as it blows away from the coast, it exposes more water that can freeze again. And so by this process of continuously blowing the new sea ice away, we can make more and more sea ice. And so polynyas are often called sea ice factories. And they are found around Antarctica, all around Antarctica, but only 4 places is enough sea ice formed to form these really dense waters that flow to the bottom of the ocean. And they are in the Weddell Sea, the Ross Sea, the Mertz Polynya, and the Cape Darnley. And Cape Darnley was only discovered in 2013. So just over a decade ago, we actually found the final source of the Antarctic bottom water. And as a result, it's the least well studied. Now, once from those 4 locations around Antarctica, once it's formed, it flows off into the deep ocean, and it becomes part of the global ocean circulation. So while this may happen in Antarctica, it actually influences the climate and the ocean circulation around the rest of the world. So in 2023, we were lucky enough to get a large grant from the Marine National Facility run by CSIRO to go down to Antarctica, to the Cape Darnley region, to study this region that we know a lot less about and why it forms in this area. Because it's a little bit different in this area, and that was curious. We're also unsure about what will happen to the formation of these waters under future climate change. And so we want to study the processes now so that we can try and predict how they might respond to future climate change. So this is a group effort. You can see there's a long list of investigators here, and it's also from many, many different institutions. So all of these voyages involve a big collaboration of lots and lots of people. And we started in Fremantle, because that's the closest port, only 11 days transit down, so a long, long way. I think we chose the furthest place in Antarctica to get from anywhere in the world. And then the return journey to Hobart is about 12 to 13 days. And so off we set, and we called the voyage Canyons, Canyons 2023. Every voyage should have a good logo. And we had scientists from Geoscience Australia, University of Queensland, Australian National University, University of Tasmania, and international collaborators from the University of Tokyo. So we had 3 questions that we wanted to study during the voyage. We wanted to understand what the properties were of this dense shelf water and why Cape Darnley was so unique. Where does it flow when it flows offshore? And then we wanted to see how it's changed through time. How has this water mass changed through time? And so we take our big blue ship down, and then we have a whole series of different equipment that we can use to study the oceans and the seafloor to try and answer these questions that we set out to answer. So first of all, when we have a voyage, we need a team. Now, this is our team. We had about 40 scientists and technical crew, and about half of them were students. So lots of lucky students got to go down. And we need people with a wide range of skills, because we're trying to do a lot of different things on the voyage. We also need our voyage mascot. And I brought Brenda along today. She sits in my office and keeps track of me and makes sure that I do some work. And so Brenda is going to keep an eye on you now for the rest of the talk. So Brenda's job was to check out all the equipment, make sure it's all working, and keep us on track. And, of course, to go down to her native home. Now, this is the big blue ship. It's 94 meters long and 7 stories high. That's hard to imagine how big it is. It's pretty big. But at the end, I'll put up an advert because it's coming to Brisbane in a few weeks' time, and there is an open day. So you can sign up to actually go and have a tour of the big blue ship. Okay? So you'll have to wait till the end. I won't put it up now. So this is what everybody always asks me when I give these talks, what's it like to be on the ship? You were on the ship for 6 weeks. Who would want to go and spend 6 weeks on a ship going to Antarctica? A few people? Anybody get seasick? Yes? No? Yes? Majority of people get seasick, and I can tell you the majority of people get seasick in the Southern Ocean, that's for sure. It can get pretty wild. So we work 24 hours a day on the ship, and we have 12-hour shifts, and you share a room with someone, so most of our rooms are bunk rooms, and we do have a toilet and a shower off our room, but basically you have 12 hours in your cabin, and then the other person has 12 hours in the cabin, so you don't have to hear anybody else snore, but you are sharing the space with someone else, and so there's a lot of making sure you don't annoy people. You're going to spend 6 weeks sharing a cabin with them. You're going to have to be nice to each other. You can also go on the website, the MNF website, and do a virtual tour of the ship if you don't make it on to the ship yourself to actually explore it when it comes on the 16th of November. What do we wear on the ship? Well, when we're outside, we have to rug up in Antarctica. It's pretty cold. So when we're just looking outside, we're typically in our down jackets and beanies. But if we're working on deck, we always have to wear helmets and fluorescent jackets. So here is myself and the other chief scientist. So we were the 2 chief scientists for the voyage, getting ready with the Cora. And you can see our fluoro jackets, our hard hats, and our work boots, which are gum boots with steel caps. Very sexy, I can tell you. Now, inside the ship, it's pretty nice temperature, so we can pretty much wear whatever we would normally wear, except when it's Funky Shirt Friday. So it's hard to keep track of the weeks when you're every day the same. So to make sure that we remember we've survived another week, we have Funky Shirt Friday. And so if you don't turn up in your funky shirt, you're sent back to your cabin to put it on and come back out again. But most of the time, we're wearing things like overalls if we're working. Here we've got some muddy overalls here to show you that we're hard at work. And then, of course, we have emergency gear. So we have to do emergency drills regularly on the ship to make sure that if we ever had an issue on the ship, say the ship hit an iceberg, it's been known to happen before, then we are ready to jump overboard, and we have to be able to put on this survival suit, or Teletubby suit, as I like to call it, in 2 minutes, so that we can then survive in freezing waters. When I first started going to sea over 20 years ago, they had one-size-fits-all Teletubby suit. I can tell you it does not fit all, because they were all built for extra-large sailors. And when I put it on, it was kind of ridiculous. So after many years of campaigning, we now have extra-small survival suits. So I might survive if we ever have an issue. What do we eat? Well, we're very lucky. We have amazing chefs on board, and they make us great food, and we usually have lots of snacks and things to keep us going. At the beginning of the voyage, we get lots of fresh food and nice veggies, but by the end of the trip, I have to say it's getting a little boring after 6 weeks, and all the veggies have run out, and we're on to frozen veggies and not much fruit. So you have to take advantage of the nice food at the beginning. I have to admit, I put on a few kilos most voyages. We've got 11 days to entertain ourselves before we get to our study area. So what do? Well, firstly, we spend a few days getting over seasickness. Secondly, we entertain ourselves by watching movies. We attempt to do yoga when it's not too wobbly. It's always a bit of a challenge. I tend to hold on to things and cheat. But we also play cards, do puzzles, and a wide range of things. And sometimes we even do some work. I like to also watch for wildlife, so we always get lots and lots of seabirds in the Southern Ocean, lots of albatrosses and petrels. Occasionally, if you're really lucky, you might spot the very, very tip of a whale in the distance. To take these photos is pretty impressive, because these things soar across the ocean, and they move so fast, and you have a pretty good camera to actually capture them this good. So these are not my photos, I can tell you that. I also like watching the waves. So on the left-hand side is us leaving Fremantle off West Australia, and as we got further and further south, it got rougher and rougher. I was going to put in a video of the waves, but I thought you might all feel a bit queasy, so I decided not to. But you can see the horizon is changing in angle here. You can see where the investigator is any time. There's a camera out the front, so you can watch the waves from your office. If you need a distraction from your work, you can pull up the camera. So this is 4:30 this afternoon. They were just off Gari, and it looks beautiful out there on the Tasman Sea. I'm quite jealous. I'd like to be out there myself. On about day 7, we hit a massive storm. We tried to avoid it, but it just kept following us. So we hit a rather massive storm, and we ended up with some pretty large waves. So this is a measure of the pitch and roll of the ship. So roll is this way, pitch is this way, and we ended up with about 15 to 17 meter waves. So that's pretty large, even for a ship 7 stories high. But we survived. And then we hit 60 south, the next challenge. Anyone who hasn't been south before has to report to King Neptune and justify why they're going south. So King Neptune comes to approve everybody who's going south. So I can't tell you any more, because that would be secret sailor's business. Let's just say it gets messy, but you only have to do it once. So having been 3 times to Antarctica, I didn't have to do it, thankfully. But all my students did, and they have now survived and can go to Antarctica without going through this again. So we like to have fun. We know we're getting closer to Antarctica when we start seeing icebergs. The big ones are fine. They look beautiful, spectacular, and are easy to spot. What we've got to be careful about is the icebergy bits and the growlers. And the growlers are the subsurface ones. And that's what they think the Titanic came down, because it hit a growler that it didn't know, couldn't see, because it was below the surface. So we have to be super careful once we start seeing icebergs, because the investigator, the big blue ship, is not an icebreaker. It is ice strengthened, but not an icebreaker. So we have to be super careful. First thing, we've arrived in our region, in our study site. So the first thing we usually do is do some mapping. Now we do this using what's called a multi-beam sonar. So you may have a sonar on your little fishing vessel. It's basically a little pinger, and the sound travels through the water and comes back at about 1,500 meters per second, and we can calculate how deep it is. Now on your fishing vessel, you just have a single beam. On the big ships, we have what's called a multi-beam, which is multiple hundred beams. And we can actually map a swath of the seafloor, which is about 10 kilometers wide at any one time. We call it mowing the lawn, because we go up and down, up and down. I actually find it super fascinating, because we are the first people to see the seafloor and what's down there. And every time I go, we find new volcanoes, new canyons. Only 27% of the oceans has been mapped. The seafloor of the oceans has been mapped. So pretty much every time we go, we are explorers finding new things that we didn't know existed. Now, what did we find in this region? Well, we knew that there was a canyon there. It already had a name called Wild Canyon, but we had very little data on, detailed data on the canyon. So we filled in some of the gaps, but we also mapped a new ridge called the Armand Ridge. Well, we got to name it. We named it Armand Ridge. So one of our chief investigators, who was supposed to be on the voyage, unfortunately died of cancer before we got on the ship. And so we named it after her, because she was a mentor to many of us on the ship. So we're in the process of making that official. So if you find a new feature on the seafloor, you can name it. How do we measure the oceans? Well, we have different tools to measure the oceans. Our main one is called the CTD, which stands for conductivity, temperature, depth. And we lower it through the ocean on a wire, and it has sensors that measure the temperature and salinity, oxygen, and a range of other things. The gray bottles around the outside collect water. So as we're coming back through the water column, we close them off, and we can collect water at different depths, and then we can analyze it for anything else that we can't measure from the sensors. The other piece of equipment that's come along in the last 20 years is called an Argo float. Now, this is basically a robot, and we lower it into the ocean, and we say goodbye, and off it goes. It floats around in the currents, it sinks down to 2,000 meters, and then comes back up, measuring the ocean as it does. When it comes back to the top, you can see it's got a little antenna on the top, sends all the data back to satellites, and we can see what's happening in the ocean in real time. So over the last 20 years, this has completely transformed our understanding of the ocean. But not just that, it's massively improved our weather forecasting, because we know what's going on all over the ocean. There are 4,000 of these floats going around the ocean, measuring the ocean in real time. And what happens in the ocean impacts our weather. So when the CTD comes back up, we have to have a sampling party, because once that water's up, it starts warming up and changing really quickly. So we have to quickly, as a team, run around and take all our samples before they change too much. It's all teamwork. So much teamwork on a ship. You can't do anything on your own. You pretty much need a big team of helpers. So we can measure what's happening in the ocean using our CTD and our Argo floats, but unfortunately, the ship's not an icebreaker, so it can't go into the sea ice. So we need to employ some seals. So here's our helpful friends. Now, you can see on top of its head, it's got a little sensor and an antenna, just like the Argo float. Now, these are big seals. This is small little sensor and antenna. Does not impact it very much. And plus, once a year, the seals molt and shed their fur, and the CTD also falls off. So this is just a mini CTD. Now, the good thing about the seals is they go into the sea ice, but they also swim around all winter when we don't want to be there. We don't want to be there in winter. That's when most of the sea ice is forming, when most of these dense waters are forming. So actually, it's doing a job for us that we could not possibly do any other way. We can only use satellites to look at the surface waters. We need to use other methods like seals to look deep. And these things dive down to 600 meters. So they're basically profiling the oceanography of the top 600 meters or even deeper of the water for us. So my student, Sienna, has just published this paper at the end of last year where she used seal data, CTD data, and Argo data to compile millions and millions of data points to develop an understanding of the oceanography of the Cape Darnley region. And so what she found is that water coming out of Prince Bay does not go straight off the shelf. It flows into the Cape Darnley polynya. That sea ice formation makes it denser and colder, and then it flows off down the Wild Canyon and the Daly Canyon here. And we get different types of, like, the density of the water is slightly different in these two canyons. So different processes that are going on the shelf actually influence what the characteristics of the water are. So we now have a better understanding of the characteristics of this particular water mass that's forming in Cape Darnley, which is quite different from the water masses that are formed in the Ross Sea and the Weddell Sea. So that's what we found. So none going down on that. How do we look back in time? So we've talked about how we measure the ocean in real time. How do we look back in time? Well, really, we need Bill and Ted's Excellent Adventures and a time machine, but we don't have that. So instead, we have sediment cores. So sediment cores are our time machine. At the surface of the seafloor, the sediments are modern. And over time, the sediments build up. And so as we go back down through the sediments, we're getting older in time. So if you know how to read the sediment core, you can tell how things have changed in the past. So here we have a schematic. We have Antarctica and our ice sheet and our sea ice. And we have sediments coming off Antarctica. Underneath the ice shelf, it grinds away at the sediment, and it pulls out some terrigenous sediment from the rocks and puts it into the ocean. And then we have different organisms like plankton forming skeletons made out of carbonate and silicate that are living in the ocean. And when they die, they fall down and they accumulate over time. Now, if we have sea ice expanding and contracting, you're going to see those changes in your ice, in your sediment core as you go back through time. So here you can see we're going from green, which is our open ocean, to yellow, which is our sea ice, and we're going back and forth. And how do we know this? Because different plankton like to live in different parts of the sea ice. So some want to be in the open ocean. These are diatoms. They make a silica skeleton, and diatoms love to live around Antarctica. So some like to live in the open ocean. Some like to be in the sea ice. And if we know what species, we can identify what species they are, we can tell that the sea ice has been expanding and contracting. But if we see the amount of terrigenous sediment coming in, we can also see if the ice sheet is expanding and contracting. And icebergs also deliver sediment to the seafloor. We call them ice-rafted debris. So there's all these different sediments coming in, and if we look at those sediments, we can interpret how this region has changed through time. So once our core comes back up, we open it up, and we have a sampling party. Literally, we turn on the music, and we all start doing our sampling. And we work together as a team to sample the core. Hundreds and hundreds of samples that we're sampling for all kinds of different analyses that we take back to the lab afterwards. But one of the first things we do is we look at the samples under the microscope to identify those diatoms. And those diatoms can also tell us how old the core is, as well as whether there was sea ice or not sea ice present. So here's 4 of the many species. There are many species in the core. Here's 4 that like to live in the sea ice. So we look for these different types of diatoms. I like to call this one on the right, on the left here, pants. It's very easy to identify because it looks like a pair of pants. But other people call it crowns and stuff. So, you get used to and learn quickly to identify the main species. Now, when we look down core, using our biostratigraphic indicators, so when diatoms used to live and they went extinct, we can tell how old the core is, but we can also see that there are time periods where there was more diatoms and less. Now, the more diatoms is when we have no permanent sea ice, so there's plenty of productivity, and we're getting lots of diatoms. So we can use this abundance of diatoms and those biostratigraphic indicators to see how old the sediment is. So this 3.5-meter core went back over 500,000 years. So 500,000 years is our time machine. Now, if we look at the different diatoms that are in the core, we have Fragilariopsis kerguelensis. I'll test you later if you can say it. It's taken me years. And we can see that that tends to dominate when we have warm conditions like today. So at the top of the core, on this side, on this this right-hand side, no, left-hand side. Left-hand side is the top of the core, that's today. So we can see it likes living today. And every time we have a warm period, we see Fragilariopsis. Whereas pants tend to dominate during glacials. So here's what we imagine is going on. In our glacials, we have permanent sea ice cover, and there's a lot less productivity and a lot less diatoms. But also, we get more dust coming into Antarctica. And pants, Eucampia antarctica, I should probably use their real name, they like iron. They like dust. So they tend to do well when we have lots of dust. Whereas kerguelensis doesn't like that. It likes it when there's a little bit of sea ice, but not too much. So we can start to interpret what's happening over time and how it's changed over time. Now, if we look to the last 2 species of sea ice diatoms, we see that they're doing something weird. We see that they are coming up and more dominant, but only in the most recent period, only in the Holocene, the last 10,000 years. So this tells us that this area has been very different in the past, because what we're seeing now is not seen back through the core. And we don't see it during these previous times where we see the other kerguelensis. So that's telling us, or at least our interpretation at the moment, and this is work done by my student Molly Hudstall, one of my PhD students, is that we've got this record of 600,000 years, but we've got a really different regime, ocean regime, going on in the last 10,000 years. And so maybe this region has only produced Antarctic bottom water for the last 10,000 years, and that maybe in the past it didn't, which means maybe this region is more sensitive to changes in the environment. And a recent conversation article came out a few weeks ago, written by some colleagues of mine, basically saying that sea ice is changing. We can see that it's changing, and that's going to influence ocean currents around Antarctica, and we're all going to feel it, not just Antarctica. And so they put together this diagram showing that if we have ice sheet melt in the top there, it starts to influence things like other sea ice, but also our ocean circulation. If we change our sea ice formation, we're going to change how much dense water we form, which is going to change how much of that really deep bottom water that we form. And of course, that all has implications for our biology. Down here, our pants, our penguins, they're all going to be impacted by these changes. Now, you may have seen graphs like this from the IPCC, the Intergovernmental Panel on Climate Change. This is the sea level graph. And we can see all these scenarios showing that by the end of the century, sea level might have risen by about 1 meter. under the high emission scenarios of 5, 8.5, maybe by about 50 centimeters under the low emission scenarios. But see this dashed line above. The dashed line above is the unknown unknowns. There's a lot of things we don't know about the cryosphere, that we don't understand how it's going to respond, how that ice melt is going to continue, whether it's going to increase. And so there's a lot of unknowns in that dashed line. And so potentially we could be seeing sea level rise much, much more significant than the current models predict, because we don't understand the cryosphere. Now, if we keep looking out to 2300, we also see these big ranges of sea level predictions under the high emission scenarios of 2 to 7 meters. Now, what does that mean? Shall we visualize it? Under 1 meter sea level rise, this image of Brisbane is how much of Brisbane will be flooded. But think about Shanghai. So we'll have about 3% of Brisbane flooded. The airport will be gone. But Shanghai will be 98% covered. So there's a lot of cities around the world, Jakarta, Bangkok, that are sinking, but also close to sea level. And so 1 meter of sea level may not sound like a lot, but it's going to have quite a big impact on a large number of people. And if we imagine 2 to 7 meters of sea level, well, you know, the river's not that far away from us here, so we'd probably be getting our feet wet. And it looks like the Australian government is finally taking it seriously with the launch of the climate risk assessment a few weeks ago. So it's nice to see that they're finally catching up. But it's not just sea level, of course. You know, changes in Antarctica, those changes in albedo, the heating up of the planet are going to cause many, many other changes to our climate and our livelihoods and our ecosystems. So that's the end of the talk, but before I finish, I want to just advertise a few opportunities. If you're interested in learning more about Antarctica, the outreach educator who was on the ship when I went down in 2023 is going again this year on the Big Blue Ship on a voyage called Cookies. Much better acronym than Canyons. I hope they eat lots of cookies. And so they're going to the Cook Glacier in East Antarctica. That's why it's called Cookies. And she's offering to do virtual tours of the ship for classroom visits and to ask lots of questions, from anything from primary school up to university. So if you have a kid in school who might be interested and teachers that might be interested, then feel free to reach out to Jolene. She does an excellent job, and she goes around and interviews all the scientists and talks about the science that's being done. And it can be any time of day or night, because the ship works 24/7. So if you have friends and family on the other side of the world, they can also join in. So she's done ones in Germany and America on the previous trip. And as I promised, this is the link that will be open soon. It's not quite open yet. I asked them to open it early, but they wouldn't. So the World Science Festival, in collaboration with the Marine National Facility, are going to be offering tours of the Big Blue Ship on the 16th of November, and it will open later in October to book a place. So finally, I'd like to acknowledge the funding for this type of research. So we got a large ship grant to go on the ship down to Antarctica. And then the subsequent research that I've presented here tonight was funded by the Australian Research Council. I'd like to thank Mike Watson, who was our amazing captain for the trip, and of course all the rest of the team who came down with us, both the crew, the technical, and the students and scientists. It really is a team effort, and I'm pleased to say that about half the team were female. So these days, Antarctic science is not just restricted to men. All the voyage leaders were female. So, you know, for younger females thinking about future careers, please consider going into marine research because there's no restrictions these days. And yeah, there are some more blogs if you're interested in reading more about the voyage. So thank you.
What an incredible presentation, some amazing visuals and some amazing research. We're going to take some questions. We've got time for a couple of questions, so if you would like to scan the QR code and pop them in. Just a reminder, we've got one more BrisScience for the year, which is November 3rd. This is our end-of-year Science Spectacular comedy science panel show, where we've got 2 teams of 3 battling it out. We've got scientists, comedians, professors, multiple universities all competing for fame and glory and no prizes. So it's going to be a fantastic evening, special 1.5 hour BrisScience, so those tickets will go on sale very soon. Keep an eye out for that. Let's get on to questions. So, one question from Will. How far back in time can you identify in the sediment samples?
Oh, actually, we can identify millions of years. And there are cores that have been, we just took what are called gravity cores, where you just kind of under gravity take soft sediments, but you can drill down further into the sediments. And so we've got millions of years of records around Antarctica. And what it shows is that actually Antarctica wasn't covered in ice until about 30 million years ago. So yeah, so we can actually study that transition into an icehouse world.
Excellent. Allah is asking the big questions. How did you catch a seal to employ?
Well, fortunately, I don't do it personally, but they go down from the bases around Antarctica. So Australia has multiple bases, has Mawson, Casey, and so they send out teams and they go onto the sea ice and onto the beaches in summer, and they these things move pretty slowly, and so I believe they use like a dart to actually just calm the seals down, and then they go and attach a little CTD profiler on its head. Yeah.
As the seal wakes up, that's the worst hangover. Okay, fantastic. A bunch of people have asked this question around the North Pole. So is the North Pole Arctic as significant to global climate as the Antarctic?
Oh, great question. So the North Pole only has sea ice, doesn't have an ice sheet, well, other than Greenland. And that's because there's no land up there. So you can only form ice sheets when you have land. It's probably equally important from a perspective of the albedo effect, but because you get this melting of sea ice every year in the Arctic, and it's getting more and more, the summer sea ice in the Arctic is shrinking, we're getting a bigger impact of that albedo effect. So it's warming up much quicker than Antarctica. Antarctica is kind of lucky because A, we've got the land and this big ice sheet that keeps it cool, but also we have a big current called the Antarctic Circumpolar Current that flows around Antarctica and actually kind of limits the warm water coming up to Antarctica. So it acts as a bit of a barrier. So the Arctic is actually warming much, much faster and is probably having a bigger impact right now on the global climate. It doesn't influence sea level so much other than Greenland. Greenland has about 7 meters of sea level stored on it, so it will still have a significant impact, but that's the only ice that's going to make a difference to sea level.
Amazing. Okay, I think I'm just trying for a couple more. I'm just trying to flick this. The questions are coming in thick and fast now. Jazz asks, besides fish and bacteria, are there any cold-blooded species living in Antarctica?
Oh, yeah. So there's a lot of really curious species. I could have done a whole talk on the curious species of Antarctica. There are these weird sea spiders and a whole bunch of organisms that have adapted to living in really, really cold conditions. Types of mollusks, like different types of crabs. Yeah, it's quite an amazing world under the sea ice and under the ice sheet. We've got videos and things. It used to be you had to dive down there. Now we put ROVs down, and we can actually explore the deep ecosystems underwater, which have all adapted to living in very, very cold conditions. Yeah.
All right. Pretty much last question. Have you actually been on Antarctica yourself? Haven't stepped on?
I've never stepped on Antarctica, but Joel has, I think.
I have. As a tourist, though, a terrible tourist.
No, I haven't, but I consider that I've been to Antarctica because I went over the continental shelf. But maybe that's cheating. Maybe I need to actually step foot on it at some point.
Well, in that case, I will ask, so that was what Mina wanted to know, but I'm going to jump to, I can't remember whose question it was, but Dee Dee, what is the most amazing / coolest thing you've seen on your trips to Antarctica? Do you have one treasured memory?
Oh my gosh, that's an impossible question.
That's a great answer. Isn't it?
No, I mean, there are some amazing scenery and amazing sunsets and sea ice and just the colours that you get on the sunsets and stuff. I did almost have a final slide with an amazing sunset, but then I thought, well, that kind of it's bright red, and the rest of the talk has been sort of blues and goes against the colour aesthetic. But yeah, you get some amazing sunsets and sunrises, and because the time that it's actually dark down there is so short, you can be on shift and see sunset, and then an hour later see sunrise, which is kind of weird. But I would say the auroras are probably the most cool thing, and you can see them from Tasmania. They don't often make it up to Queensland, but I think seeing the auroras is pretty cool. That's for sure.
It's amazing. Now, Helen is going to be hanging around for a little bit. Come up and ask questions if you want to. Kids, are you?
Yeah, I have some stickers from the voyage, so if anyone would like a sticker, come up and ask a question. You can have a sticker, part of your telling your friends about why Antarctica is important and why we need to care.
And that's not just restricted to kids, just to be clear.
Yeah.
Could you please join me in thanking the amazing Professor Helen Bostock?
Thank you. Thank you.
Please stick around, have some food, and we'll see you next month for the final of the year.